Good afternoon, Putala.
Good afternoon, sir.
Today happened to be the lesson 3 because for this time, 2 sessions, one thermodynamics and another subject, scheduled for the same timing, so we couldn't do last week. Sorry about that. Anyway, today 11 December 2021, our third lesson of thermodynamics. So I welcome all the 202 or B2 semester 2 manufacturing, mechatronics and BST batches. Okay. We have 2-hour time schedule, so we will see how we can proceed with the subject. Right? Lesson 1. You got a little idea about space. We came until this. So your point here is recognizing a space, mainly in thermodynamics application. So this is the main point in the lesson 1. So we will come to the same point for the lesson 3 as well. So the lesson 2, this is the lesson 1 again. Lesson 1. Yeah. So we came to know about the space. In the lesson 2, we discuss about some refrigerant. And we couldn't finish this lesson 2 in style because of the 2-hour time limitations. But you got little idea about this, what refrigerant means. And about the safety data and the technical data sheets. And you have realized that even water is a kind of refrigerant. And there are technical data sheets as well. And you came to know about the gauge pressure and absolute pressure. So we will look into the gauge pressure and absolute pressure again today. After that, we will continue. So very interesting. So today I just make this slide for you. I believe you can say this. Water boiler. These are actual pictures. These are actual pictures, and I need you to recognize the space related to this. Okay, recognizing, identifying the space. So let me draw a little schematic. Let me draw a little schematic. If the space is a kind of a cylindrical shape, like a can shape. Both it seems. Can shape. And then here, it's easier for me to take the side view. I will take a little taller. Okay, this is good enough. Same size. So there can be two portions. Two portions. So one, the water filled with water, one portion should be filled with water. This is the one. The other part, it's a space containing water and steam both. Sorry, steam and air both. I'm sorry, steam and air both. Yes, something like this. So in the boiling water, boiling takes place in water. Okay. So there can be heat interactions. Heat interactions means underneath. Yeah, because of the flame. Because of the flame, there is a heat transit towards this water body. True. So this is at the boiling state now. Okay. While receiving heat by water, there's a release of heat. Heat losses from this side. The reason is at the boiling, this is at 100 degrees Celsius. You know this. 100 degrees Celsius. (100°C). So now, right here, boiling takes place. So, same way, there is a heat loss as well. heat loss as well. And then this losing of heat is, of course, another way from the top here. You can see the losing of heat because ambient is quite lower temperatures and the surface is 100. So there can be numerous ways of losing heat. Okay. Side view also. Let me mark it. Losing of heat. Space boundary. I'm going to do the space boundary now. Let me try a different color. Yes, interesting. Space boundary. So within the boundaries, the space of our concern. Even outside the boundary, maybe the metal pan. Metal pan. Here. Imaginable space on top. Interface. A surface. Interface means the face that is demarcating the system and outside the system or space of our consideration and outside the space of our consideration. So here we call this thermodynamic system. Later we will learn why this is called thermodynamic system. System. Maybe almost the same size. Good. Interesting. Okay. Heat losing from here as well. So recognizing the space in thermodynamics application, it is very important, really important. So once we recognize the space identified with the boundary, you know what is the system and what is outside the system. Okay, this is system. Outside we call surrounding. Okay, surrounding. So if I mark the surrounding, Let me try. Yeah, I'm not sure whether I can do it or not. Maybe later I will do it. Here, no much of space. So I will write here. This is the system. System of our interest. This is the system of our interest. And always, system has interaction with its outside. Otherwise, it's an isolated system. But generally, most of the thermal or thermodynamic systems, there is a connectivity with the surrounding. So let me put the word surrounding here. Just for you to feel this. Good. Surrounding. Here also, I put surrounding. Everywhere outside the system is surrounding. Okay, everywhere outside the system is surrounding. So, system together, the surrounding must come to your mind. Otherwise, it's an isolated system. So with the system, the surrounding is a must to come to your mind. Even this boiling, okay, this water boiling. So your surrounding. Here, some high temperature zone here, sideways exposed to ambient on top. You can imagine an interface above which belongs to the surrounding, and below is the water boiling, the water body or the system. Good. So I feel you have some idea. I feel you have some idea. So here you can notice that with the surrounding, heat interaction, heat comes in. Even heat loss means heat goes out from the system. First come to the system, then go out from the system. Heat go out from the system. You may say that heat losing, that is okay. The losing of heat. Okay. Then, other than that, here the point is mass or steam means originally in the water, but it evaporates. Means there is a mass interaction with the surrounding. Evaporating water means turns to steam and go into the surrounding. It's an interaction. So the system is losing its mass. System is losing its mass. Okay. Just recognize this. So there is a mass transfer as well. A mass transfer. Transfer means from system to surrounding. Mass transfer as well. Mass transfer as well. So that's how the connectivity of the system with the surrounding. Heat interaction and mass interaction. Mass interaction. So mass transfer is from just from one surface only. The other surfaces, no mass transfer. If mass transfer is here, means the leakages. If there is a hole or holes in the pan, you can see the water leakages. So that is not the case here. So only the evaporation takes place. Okay. The point is here, let me duplicate this slide. When water evaporates, system boundary changes. And this is your pan, the remaining. See, originally up, finally. So sideways boundary change. Okay. The system volume change. So here also the same. Become like this. Okay. I just draw this, everything surrounding. So this is surrounding. This is surrounding as well. So heat transfer takes place. So losses takes place. Now the thing is, in this type of water body, you can see the boundary is also moving. Okay. The boundary is also moving. So observations of thermodynamics system. So thermodynamic system. You should know that. That is not clear. Yes, system. Is there, but surrounding is also there. System plus surrounding. Okay. You have to recognize this. Otherwise, you will miss the thermodynamics analysis. So, system and surrounding demarcation. Demarcations between system and surrounding. We call this system boundary. And could be an interface. Interface. In the sense, here you can see the interface. Just, it's kind of imagined one. So that's why sometimes you have to see from the mind, the interface, the interface. Even the heat transfer, you cannot see heat transfer, but from you, lifelong experiences, you know that such heat transfers are possible. Same with such mass transfers. Here it is evaporation is possible. Okay, that is very important to note. So heat transfer interactions. Interactions means system and surround. The system and surrounding. Mass transfer means moving masses from one place to another. So it's transfer. Mass transfer. Interactions. Lose by the system or lose from the system, gain by the surrounding. Again, between system and the surrounding. Also, there is a possibility of moving system boundaries. Possible. Not always, but depends on the situation. The way you are looking at the system, the way you are taking the system. So this water boiling is a very good example of that. Okay. So basic understanding of thermodynamics is actually quite natural. Quite natural. So I believe you have a little understanding on this. Good. Again, water boiling. Same like in the previous one. You can see water boiling. Here. The left side figure. Originally, lid is closed. And when the lid is open, they can see full of moisture. Here, no such. because all the time releasing, it is not that visible, but here you can see some moisture is trapped and release. The same, trapped and release. The kettle also the same. So you may feel that, yeah, compared to this free boiling of water, when you close the lid and boil this, there is something significant difference. Okay, what the difference? Yeah, we have to recognize there is a significant difference. I think it is quite interesting. So we will take this example. Water boiling. Lid closed. Lid closed. Not fully closed. Now the situation seems different. The same. The same system. The same system. Now it is different. Your boundary. System boundaries. Until here, you can see a system boundary. Let me see how well, sorry. The system boundary. Is this the system boundary? Still you have some escape. Escape. It is something like here. You have a vent here. From the vent, the moisture escapes. Then also the same. Interesting. Now it's like this. I think you can recognize this. Now, a little vent here for moisture to escape for this case. This is no more the model. See now, the boundary changes, means your surrounding is different. Surrounding is different. Okay, even see the free boiling with open on top, or this nature of this is the closed one. So you can see the system boundary changed. Okay, system boundary changed. So heat transfer, I will take from here. Heat transfer, I will take from the system boundary to outside. Like this. So similar application, but completely a new system. So here, liquid. So now this is still 100 degrees Celsius, but now the system is until here. So you have liquid and vapor. Liquid plus vapor. That is the point, okay? So in thermal applications, so previous one is only liquid. This one is liquid plus vapor, both. All water boiling, true. This one, system is only liquid. Liquid only system. Vapor portion belongs to surrounding, because vapor continuously evaporates and it is something like out of our interest, this releasing of moisture or vapor here, steam. So only liquid is our interest, but this case, yeah, we may need the boiling liquid, but the application suggests it's different. The vapor is trapped here. Vapor is trapped. So vapor also 100 degree, liquid also 100 degree, let's say. If no much, little pressure rising inside. So same temperature, liquid plus vapor. nearly 100 degree. There may be 100 point something because of the pressure buildup, but same pressure, same temperature, liquid and vapor. Of course. More liquid and less vapor. But you can see here, the liquid and vapor mixture is. So if we look into the same type of writing, for this case, good. System plus surrounding. Still valid. System plus surrounding. Demarcations between system and surrounding. System and surrounding. Demarcation. You can see. Heat transfer interactions. Same. But now it is different. So here, heat transfer, here heat transfer, but heat transfer interaction somehow. So that phenomena is the same. Mass transfer interactions. See mass transfer interactions. Releasing mass. Same. So here, moving system boundaries are possible, but here, for this case, system boundaries not moving. For this case, system boundaries not moving, but water level or the liquid level or the water level is dropping back. System boundary no change. So moving system boundaries are possible, but in this case, there is no change. Okay. So the volume of the system is the space of our interest of the thermodynamic system. Even outside the space of our interest is another space. That's also our interest as well. Space of the surrounding. Yeah. You may feel that you have understood something. Okay, you may feel you have understood something. That is interesting. So here you may notice that there are two-phase systems. Two-phase. Liquid plus vapor. Okay, here liquid plus vapor here. Two-phase system. So this is the one. Two-phase system. Okay, good. Then you know that water boils at what? 100 degree? Celsius. I will add a special word here. Because water can boil at different temperatures. So I will add a word here. Normally. Normally boils. So normally means under, or let's say, I will take the word out under even. Atmospheric conditions. So here, the pressure is important. Normally boils. So that's why normal boiling point of water we call approximately 100 degrees Celsius. Normal boiling point. Okay, good. So very interesting. Boiling and evaporation are two things. Huh? Even in boiling, evaporation takes place, but boiling is something taken place forcefully. What if? What if? Water normally boils at 20 degrees. What if water normally boils at 20 degrees? So this is Basavakulama well. Basavakulama tank is over 2000 years old tank done by Kingston. Okay, I just put this. It's a very nice picture here. Basavakulama water tank done by Kingston. See, they can do this. What if water normally boils? Means the other way of asking this question is, what if NBP of water is 20 degrees Celsius? Do you know the Basavakulama tank area? This is in Rajarata area. Rajarata means the Anuradhapura. That side, generally, ambient temperature is always above 20 degrees Celsius. In this area. So we are over water. So we have to consider that locality for this Basavakulum in Anuradhapura. Ambient is 20 degrees Celsius. So what you can say? If NBP is 20, of course, no water is here. There is no water if NBP is 20 here. Okay, there is no water if NBP of water is 20. There is no water This was muted for a while. Sorry about that. Now you can see this. And if you still need water, we have to keep water pressurized. But still, when exposed to ambient, that evaporates. So, what is NBPF water? NBPF water, 100. So, until the ambient become 100 degrees, that is not possible. We will not. Humanity and even the world will not be there until 100 ambient temperature becomes. So until the ambient becomes 100, somehow maybe control ambient, 100 degrees Celsius at atmospheric pressure. Till then, water remains as water. That's why. So water freezing at 0. So 0 to 100, we have liquid water. 0 to 100. So quite a wide range. So we can see 0 to 100. So we can have water all the while. In low temperature environment, we have little bit chilled water. In temperate environment, it's, let's say, in the 30, 40 degrees Celsius, sometimes in the summer times, water is warm, but still in liquid. Okay. So you may feel it is nothing, but we should not think in that. This is miraculous availability of water and having such feasible temperatures. Okay. Because of this, we are existing. So people are going to the planets and they are looking for water. Water can be in the atmosphere, but if water is not on the ground in liquid form, impossible to live. So in different planets, there may be water in the atmosphere. We may not know. Depends on the gravity. So it depends on their gravitational or the pressure conditions. Our pressure conditions, we have water in liquid form on the Earth. But some planets may be under very low pressure conditions. On the planet surfaces, there may not be water possible. Okay. So substances are like that. So depends on the ambient condition. Their formation or their forms or the type of existence can be different. Okay. Interesting. So let's go back to lesson 2. Lesson 2. So R290, I think we have discussed NBP. Yeah. Normal boiling point is minus 42.1. That's why. So at the ambient condition, so this is well below the ambient temperature. So R290, it is not possible to have in liquid form at ambient condition. So R290, we have to keep pressurized. This is the point. So we have to keep water pressurized. If normal boiling point is 20, because ours is about 20 ambient. So now if we look into this, okay, minus 20.1, 42.1. So if we need to have our 290, this are 290. In liquid form, now we are talking about ambient temperatures. R290 should be pressurized. So you have under high pressure, you can have liquid, but once exposed to ambient, ambient is low pressure, means a normal pressure. Once exposed to ambient, it's normal pressure. The temperature is well above minus 20. So this will turn into gas form. If the ambient is below minus 40, of course, this will remain as liquid. So if the ambient at normal pressure is minus, let's say 43. We can have liquid R290 in our water glasses. Glasses. But at minus 43, water is frozen. Water is frozen. That's the case. So we have to keep water being heated to make it in liquid form. So I hope you can understand the importance of boiling point. So we have to keep pressurized. We just got this from internet. You know this is a gas cylinder. So here we know that this gas cylinder is pressurized. Gas is pressurized. Gas. Inside the cylinder is pressurized. is pressurized. To keep in liquid, to get stored more mass of, let's say, R290. R290 is butane. Sorry, R290 is propane. Okay. So we have to keep the gas pressurized so that we can have liquid. The reason is simply because normal boiling point is very lower than ambient. So when this comes out from the hose, immediately turns into gas form. Okay. Unless ambient is below normal boiling. Okay. So I can put in this gas cylinder for propane is not really correct.
So screen is not shared.
Yeah, with that. Screen not shared.
Screen is not
Okay, sorry. Yeah,
shared.
yeah, sorry. So putting R290 for the cooking gas is, it is not really good. So let me put the propane gas. It's different. Propane gas cylinder. So those are for the very special usages. So this is the propane gas cylinders. So maybe for some industrial applications, not for domestic. So that's it. Even oxygen under normal pressures, normal ambience, oxygen in gas form, because normal boiling point of oxygen also very low. So whenever normal boiling point is lower than ambient, okay, it's in gas form. What's the normal boiling point of pentane? Normal boiling point of pentane. Is 36.1 degrees Celsius. New slide. Sorry. I will take duplicates. Pentane. 36.1 degrees Celsius. And you can see that it is above 36 ambient. It is in vapor. So around ambient condition, you can see at ambient, certain volatility is there. Volatility. Is there. Volatility means even if there is a little wind blows, maybe little evaporation. Volatility or evaporation is there. Okay. And this pentane means this is petrol. So that's how when you are selecting fuels, so it is very important to look into this normal conditions and then the boiling points. So diesel means heavier, no evaporation. Kerosene maybe it is little heavier than petrol. Okay, so this is in, so 36 means mostly in liquid form. Is there, but mostly in liquid form. But you can see little evaporations. So still you need storage. You no need that pressurized maybe, but if 40 degree, this becomes vapor. So still need careful storage and transportation. Okay, because this also costs fine. Interesting. Okay, quite interesting. Yes. So, what example? Imagination. This is a true case. Another true case. Now, I'm going for the water. Back to what? What? (100 degrees Celsius). So, still you have the safety data sheets. But now the point is 100 and above applications. This is in applications. Thermal applications. Or let's say thermodynamic applications. So needs above 100. Above 100 degrees Celsius. So we would say well above 100 degrees Celsius of evaporated what we call the steam above 100, because it refers the boiling point. Okay, now and when above 100, The other point is when at the temperatures well above 100 to keep water in liquid form, you need a high pressure enclosures. You need a high pressure storage or equipment to handle water, because above 100 at normal pressures it's evaporating. So well above 100 it is already vapor. So if you need to have still in liquid form, you have to have high pressure. That's why the boiler applications consider high pressure. So I'm really generalizing this knowledge. Yes, pentane petrol boiling point is 36.1. Yes. Yeah. That is a good point, good question, Pruta. In the chat. So I will put the question in the chat. See, now we are thinking. Very good. The question. The boiling point of pentane or petrol is 36.1. So if the area temperature is greater than that, how the petrol is injected to vehicles in liquid state? Yeah, vehicles in inject. So this is, by right, should be a high pressure system. This should be a high pressure system. Pressurize it. So when you pressurize this and release to lower pressure, okay, release to lower pressure, there could be atomizations and even can be turned into gas forms. Again, this is a matter of balancing. Okay. So as an answer, I will put this way. An art of balancing the pressure and temperature in combustion. Okay. An art of balancing the pressure and temperature of fuel flow and injection in combustion applications. There's an art. Art means it's a state of the art. State of the art means some technologies, those are more like creativities, related to creativities. Later you may be doing the modeling or whatever the recognition of the technology. Initially, this comes as the art. So art of balancing the pressure and temperature, fuel flow and injection in combustion applications. So I would say that way. Yeah? So it's very interesting. There was a time, no petrol, this injection systems, only the diesel. But here, now we have the petrol injections. So immediately after injections, effective combustions may be turning into the droplets and immediate gasification. So more surface area for combustion and maybe more micron particle than the carburetor effect. Carburetor, you have the gas, the vapor form only. But here in the injection, you have more turbulent and more fine particles, and there can be an enhanced combustion effect. Yeah. So when it comes to combustion, in advanced combustion system, still the art is being practiced. Still there is an art which is more than science. That's why in Japanese vehicles, the same petrol you are using, and the Chinese engines, the same petrol. The performance different, efficiency different. European vehicles, their approach is different. They have better combustion, more powerful. But Japanese, better combustion, better efficient, but optimal power. Okay, so you don't get heavy engines in Japanese vehicles. Okay, so those are more optimized. But combustion technology is something even we can try. Even we can try. Yeah, vaporize in petrol storages, another problem. Another question here. So just the answer maybe. It's the question maybe bold. So one more question here. Yeah. Actually, this one, even I had to explore this, but we have to assure that there should be no vapor traps. That is very important. So no vapor traps. That is very important. So avoiding vapor traps is also an art. Art involved storage solutions. Okay, storage solutions. So vapor traps. So here I don't think vapor is being released to outside. I don't think so. But still, no vapor traps there, or no vapor voids there. Because vapor voids, vapor traps, if mixed with air in the proper ratios to have the sufficient oxygen for the combustion, and even there can be some sparks, we may not know, even during lightning, sparks possible. So these are a must to avoid. So there should be proven techniques to that, but you know how dangerous it is. So one is, of course, the systems should be isolated. That's why I think even in petrol stations, the petrol storages are underground. Means it's in complete isolation. Isolation means with the surrounding, fully separated. Assure knowledge that is true. Even there should not be any transfer of static charges. So even static charges can be a risky ones. Give me a second, Putta. Yeah, Putta. Okay. So we will explore on this. But at least now we can think about this. Now I'm going to refer you to the steam tables again. Okay, better before steam tables. Another topic. Sterilization. For sterilization, steam can be used. Again, I got this picture from internet. Sometimes we have no choice, but we need to get some from the web with no permission, but no choice. Why I need to make it bigger? Yes. So this is a steam sterilizer, a high pressure. So those who are working on food processing applications, you may know better about this. This red circled one is the pressure gauge. So here in this applications, the pressure applied, because example in the food, the pressure, the food, you are using this, but you are not raising the temperature extremely high, because too high temperatures means too high pressures. So here inside you can see water and steam. Water and steam at high pressure. So you can see water and steam at high pressure. So water and steam at high pressure means water and steam together. So we would say that water and steam at high pressure means saturated water and steam at high pressure. Remains to be, if this is being in operation, let's say for one process, so at a constant pressure, so you are maintaining this, so quite stabilized at a certain pressure, both water and steam they are together, so that is saturated. So later we will understand what saturation means. Okay, so what saturation means, you should understand everything. So even a simple word, you cannot just take it for granted. You should understand what saturation means. So here, there is a balance. If one drop goes to the steam side, similar mass comes back to the water side. So there is a balance. Okay. So it's a kind of saturation water and steam at high pressure. So I'm focusing on the pressure now. Pressure. For the normal application, we call 15 psi. 15 psi gauge. Okay. Or we call almost 1 bar. 1 bar. Okay. 1 bar. What is gauge? What's the temperature? Is around, later I will correct it, around 121. I may be right, I may be wrong. If I'm wrong, I will correct it. That is around 121 degrees Celsius. Maybe around 120s. Okay, around 120s. So now, what I'm going to look into is, I'm going to look into the a bit noisy. Your continuous assessment, I will go to the steam table. So I mentioned you that the sterilization temperature is 1 bar, and I just guessed this as 121. So let's say how this is possible. Okay, so you are going to learn something good. See, pressure 1 bar. I mentioned temperature 121, but here this is 99.6. So I will check the temperature 121. Ah, yes, here. Okay, here 121.8. So let's say I change this to I change this to 120. 120. Okay, 120. So 1 bar gauge. So let me go to your steam table. This is the one. So 1 bar gauge is something different, but here at least pressure at 1 bar, you can see temperature is 99.6 degrees Celsius. Okay. Here I can see 120 is here. 120. 2 bar. So 2 bar, it is 120. So at the steam table, 2 bar 120. So I will take this. I will copy this. And I will bring this to your notes. daily notes. So I'm going to paste it here. Sorry for the noise, Putala. Okay, good. So picture here. Now see the point. What I'm going to explain. Water boils at 1 bar at 100. So 99.6 here. So atmospheric is in between, it is around 100. So this see the atmospheric pressure, because atmosphere has its own pressure. It is very simple. You have this Basava Coulomb tank. So I just make this here. If atmosphere has no pressure, water cannot be kept like this. Understand? If atmosphere has no pressure, if zero atmospheric means everything vaporized, you cannot see liquid. Most of the time, maybe. You cannot see many of the liquids. So it is impossible to imagine zero atmospheric conditions. So atmosphere itself produces a pressure, which is very useful. Somehow the nature subjected to that pressure, and reason of having this kind of lakes also become possible because of this pressure. Okay. So at this pressure, when the water, you heat it up, when you heat it up, water, your water boils at 100. So this one is for this atmospheric condition. Thermal application, okay, heating of water. Okay, this is the one. So this atmospheric condition, heating, is relevant to this. So I will just put it here. Okay. But this 120, here gauge pressure is 1 bar. See, 1 bar gauge pressure. Temperature is 120. Okay. 1 bar gauge pressure, temperature is 120. But in the atmospheric pressure, at 120, this is 2 bar. So for this case,
One bar.
this is the one. Yeah, Puta, anything? Okay. Yeah, time is reaching. Yeah, you can send the invitation. Sorry, your registration numbers. That is fine. So here you can see for this case, I will take it again. Pressure PSIG 1 bar is gauge temperature 120. But at steam table, at 2 bar, 2 bar means 1 bar gauge plus 1 bar atmospheric. Okay, so table at 2 bar means 1 bar gauge, 1 bar atmospheric means 2 bar absolute. So in the steam table, so you may see the pressure as 2 bar. That is the absolute pressure. That is the absolute pressure, this P bar is. So let me go through this. So lesson 3 today, thermodynamics. Okay, 220 B2 semester 2. All the 3 batches, 11 December. So still we are focusing on the thermodynamic systems. So considering the boiling application, we have recognized the space. The very first knowledge we have received in the very first lesson, lesson 1. So space, and outside the space relevant to the system, thermodynamic system. And outside is the surrounding. And you have noticed the system boundary. Okay, system boundary. And we can see that this system boundary is not fixed. That's a movability. So thermodynamic system. Some features you have recognized. System to be considered together with the surrounding. If no consideration means isolated. Some systems need isolations. Example, the petrol storage in the sheds. Okay, in the sheds, you cannot monitor it. So you have a permanent solution. So underground may be concreted, well sealed, but somehow when petrol pumps, there should be a way of equalizing the pressure to make it not going into vacuums. So those need some technologies as well. So systems, system boundaries, heat transfer interactions with surrounding mass transfer interactions, and the possibility of having moving boundaries. This water boil, simple application. So you have realized that. Again, the thermodynamic system. And 2 phases, we came to liquid and vapor. And understanding of normal boiling points, we have done it to the fullest. So we know how the gaseous form substances at normal conditions. To keep it in bigger masses, you have to put it under liquid form. So you need to apply very high pressure on that. So that's why R290 like applications, you need high pressures. But when it is exposed, it is immediately become gas. Because ambient is 30 plus, your normal boiling temperature is minus 40. So there is a huge temperature rise. So converts into gas immediately once come out from the cylinder. So cylinder constructions, we will discuss later inside how that should be and all. So propane, Again, normal boiling point. You see how important this knowledge. Even for pentane, there are safety data sheets, very important, same like water and R290. And there are material data sheets. You should be familiar with those when you are dealing with substances in the field, in the jobs, in the industries. So it is good to have thorough understanding, because that understanding makes your work and your output different. Even you can save lives. You can save the resources. You can contribute for the qualitative outputs and also for enhanced productivities. So thermodynamics is something like a pretty much practical knowledge. So that's why I need you to do that part. The one-time note and CS, I'm contributing in this way, finally all for the same goal. So here, again, understand the absolute pressure. See, at 2 bar 120 degrees Celsius, you do sterilization. But if you really see the gauge, this is 1 bar. Your temperature is 120. 1 bar gauge, 120 Celsius temperature means 1 bar gauge plus the ambient pressure is 2 bar absolute. That is what you see in your steam table. So don't get confused. So open boiling is ambient, under ambient atmospheric pressure, that is 1 bar. Zero gauge, if you just put a gauge here, it reads 0 reading. Okay, unless it is calibrated to show 0 as 1, just to see the absolutes. But generally gauge pressures, don't get mistaken, gauge pressure is gauge pressure and it shows 0 absolute. It's a gauge pressure. The real pressure inside, okay, plus the absolute, you have the table, the absolute pressures, plus the ambient atmospheric pressure, you have the absolute. So this is today's discussion. So connected with some practicalities. So you know how important connecting your knowledge to the practical applications. That is very important. So I take very simple ones because some are manufacturing, mechatronics, BSTs, different applications. So it is very important to have the essence of knowledge. So we no need to go for the heavy technology applications yet, till understand this kind of even reading of this. Maybe next week we will look into further understand this. And also one more thing I have to mention, Nibutala. I have a very special facility, virtual facility, to teach you refrigeration technologies. I have a very special virtual facility. So I can teach the refrigeration technology very well with this for manufacturing, mechatronics and BST, for pretty good professional level understanding in very easy manner. But this one, we will have separate sessions. Okay, we have to have separate sessions because if not separate sessions, it is very difficult to, I'm going to show you that without having a separate session, it will take up the thermodynamics time. So I'm just showing you that facility. See with the, yes. Internet bit slow today. Oh. Today signal seems so finally it is loaded. Let me save the attendance first. So here you can see many courses. So we can look into all related to refrigeration. So if you want to learn on the refrigeration systems, so there can be systems. This is the system components. So we can discuss about the components. Let's say about capillary tubes. So you have to learn this. So there are some steps, learning objectives. So we have to look into this. And even we have the pre-test, how to know about the capillary tubes. Then even the post-tests and the reading materials. Even reading materials, the interactive learning. Loading may be slow today. So there could be many such. So you can learn about the real systems. So this is mainly on the refrigeration. So this may take maybe 10-20 hours extra. So we will have a separate session for this Putala. So we cannot use the thermodynamics time for this. This one example only. It's loading, but very nice 3D interactives. So we will find the time for this. It's loading very slow today. Even background theories. Everything is here. So this is as a see the background theory is all here. So we can, at least I can pass you the reading material so that you can have somewhat realistic applications on refrigeration. Should be very useful. Even 3D animations, see?
Excuse me.
Yeah, Buddha.
So excuse me.
Yeah.
So අපිට මේ 3:30 ට lecture එකක් තියෙනවා.
Right. Okay, Buddha. Okay. So we will stop the class then. Thank you very much for joining. So see you next week. I will send you today note and the recording. Okay. See you then. Bye. Bye.
Thank you.
Thank you, sir.
Thank you, sir.